All right, so we're going to continue today, finish up this discussion of structures here by introducing what's called Vesper theory. Okay, we talked at the very beginning about these ionic compounds and how ionic compounds are kind of boring from a structural standpoint. They're just repeating arrays of positive and negative charges, and that's true for all ionic compounds. But covalent compounds, because of the nature of covalent bonding, are a little bit more interesting. We've been describing those molecules using these Lewis structures, right? Those Lewis structures show us which atoms are bound to who and where these lone pair electrons live in our structures, okay? Those Lewis structures, though, they just tell us this bonding information, right? Where electrons live, who's bonded to who. They don't tell us about the shapes of the molecules. And that's what Vesper theory is here for. This is now going to help us understand the shapes of molecules. All right, and this theory, Vesper, stands for valence, shell, electron, pair, repulsion. Okay, and really the key word here is this repulsion idea. All right, and this is going to be this underlying theory behind the shapes of these covalent molecules. The idea that these groups of electrons are going to want to be as far apart from one another as possible, because electrons are all negatively charged, and opposites, or rather like charges, repel one another. So these groups of electrons around our central atom are going to try to be as far apart from one another as possible, and that's what's going to dictate the shape of that particular molecule. All right? So let's take a look at a simple example here. Okay, and for right now, you're just going to trust me when I talk about this molecule. All right, this molecule as of carbon dioxide has carbon, and it's got a double bond to 2 oxygen atoms. All right, and so if you were to look at the shape of this molecule here, you would see that just like in our Lewis structure, you have a carbon atom sitting in the middle. And it's bound to these 2 hydrogens, to these 2 oxygens. And it wants those oxygen atoms to be as far apart as possible. So it points them in literal opposite directions, right? So keeping everything as spaced out, as far apart as possible, leads to the shape of this molecule, what we would call a linear geometry. Okay, so the geometry of a molecule is dictated by this idea of electron repulsion, the idea that these covalent bonds made up of electrons, these want to be as far apart as possible in my molecule. All right, so that's the basis of this Vesper theory. Pairs of electrons, these bonds, as far apart as possible in our molecule. So it's kind of easy enough to understand here when we just have these 3 atoms, but we want this to be generally applicable, all right? So the first thing that we're going to need to do before we can understand these Lewis structures that we've drawn is we need to learn how to look at them and figure out the number of what are called electron regions. Okay, we need to, and actually we can even say, we need to count the number of electron regions. Okay, so given a Lewis structure, let's just take one of the first ones we picked apart here, water. We need to be able to count the number of electron regions in this molecule. And specifically about that central atom. Right? Your central atom is what's going to dictate the overall shape of the molecule. Okay, so the number of electron regions, we have to draw our Lewis structure first, right? So this is something that we interpret from our Lewis structure. It's going to be the number of lone pairs plus the number of covalent bonds, okay? And then importantly, this is of any order. So a single bond, a double bond, a triple bond, these are all considered just one electron region. All right, so for my water molecule, again, the only thing I'm looking at is the central atom, and I'm going to count the number of electron regions about that central atom. Okay, so I have 1, 2 lone pairs. So my number of lone pairs is 2. Plus 1, 2 covalent bonds, bringing me to a total of 4 electron regions. All right, and so we'll talk about how I'm going to turn this into my geometry here in a second, but this is the one skill that we need down first before we can move on and look at geometries of molecules, all right? So before we go on, I'm going to put down a few more structures, and you're going to count the number of electron regions in those molecules, in those Lewis structures. So for these 2 Lewis structures here, let's take a second and count the number of electron regions. All right, so this first molecule here, this is actually what's called formaldehyde. Very commonly used molecule, especially in the preservation of dead stuff. Fun fact. If you've ever dissected anything in a biology class and it's got that ridiculously overwhelming smell, that's this guy right here. All right, okay. So first of all, number of electron regions in this molecule. What do we got? What's the number here? Throw it out. We're looking just about the central atom, and we need to count the number of electron regions. There are no lone pairs, because again, I'm only looking at that central atom. That's what's going to dictate the geometry of my molecule. Plus the number of bonds, all right? But importantly, we're counting bonds of any order as just one electron region. So this molecule here has 1, 2 single bonds, but this double bond I'm going to count as just one electron region. All right, I'm not counting individual bonds, I'm counting bonds of any order. So this molecule right here would have 3 electron regions. Yes, there are lone pairs on that oxygen, but that's not my central atom. That's not going to dictate the geometry of my molecule. All right, and that double bond is just 1 electron region. All right, so what about in our nitrogen trifluoride here? How many electron regions? So we got 1, 2, 3 single bonds, and then this lone pair makes a total of 4 electron regions. Okay, so given a Lewis structure, right, the first step here is always going to be to draw your Lewis structure. Once you have your Lewis structure, we can use that and interpret it to figure out the number of electron regions. Okay, this is important because this is going to uniquely point to what's called the electron geometry. So we're going to make a little cheat sheet chart here. Number of electron regions. Hybridization and electron geometry. All right, so if you have 2 electron regions, like in our first example, carbon dioxide, right? About that central atom, there are these 2 electron regions, okay? This is classified as a hybridization of what's called SP, and this electron geometry is linear. Okay, and again, that's all everything in a straight line. All right, if we have 3 electron regions, as was the case for our formaldehyde, this is classified as an sp2 hybridization. Okay, and this geometry is what's called trigonal planar. All right, so let's take a look at the shape of these types of molecules here. This would be an example of a trigonal planar molecule. Trigonal, you can see because it makes a little triangle, right? And planar because all of those molecules, or rather all of those atoms, all lie in the same plane. You see this molecule here is completely flat, right? You could take one slice and slice through all 4 of those atoms. They lie in the same plane here. So again, trigonal planar. Okay, so that's what we would call it with a molecule with 3 of these electron regions here. If we had a molecule with 4 electron regions, that would be considered sp3 hybridization. And these are what are called tetrahedrals. Okay, a good example would be CH4. It's got these 4 electron regions here. All right. A tetrahedral is how you can arrange 4 things in space such that they're all perfectly spaced out from one another. All right, if we want to take a look at what that would look like, why isn't it an option? Of course. God damn it. Of course, this is going to be the only one that doesn't work. Fantastic. All right. I don't know. It won't open that program. A tetrahedral, okay, you have these 2 bonds that are spaced out. All right. Then you have 1 bond coming out of the page at you, and then another bond that's pointing into the board. All right, so these are these perspective drawings of these geometries here. All right, the straight lines, these are flat on the page. These wedged bonds are pointing out of the page. And these dashed bonds here are pointing into the page. Okay, this is how we can sketch these three-dimensional objects. Because again, whenever you do your Lewis structure, it's kind of a flat representation. But these things are 3D shapes here. So we can use these perspective drawings here to help draw our 3D shapes. I'll post a video, so like link a YouTube video that has these tetrahedral shapes. It really helps to be able to see them in that program where you can spin it around. Of course, I tested everything out right before I got here, and for no good reason, it's not working. So, all right, well, I'll sort of link something so we can get a better understanding of what these tetrahedrals are. Okay, let's stop here for a second and go back and review. So these are our electron geometries, and we're going to distinguish here between two different types of geometries. An electron geometry this is the shape of the electron in space, i.e. where bonds and lone pairs are pointed. But then we're also going to talk about the molecular geometry. And this is the shape of the bonds in space. So only bonds, not lone pairs. All right. So if a molecule has no lone pairs on that central atom, then the electron geometry is simply equal to the molecular geometry. Okay, but if there are lone pairs on the central atom, then these will not match, because again, our electron geometry is concerned about where the electrons are pointing, but molecular geometry is only bonds, so lone pairs are invisible in our molecular geometry. Okay, so if we take two examples, one that we did before, and then we'll do a different one. Okay, these two molecules here, they both have number of electron regions equal to 3. Right? If we count the number of bonds and then of any order and the number of lone pairs, we would find that both of these molecules have an electron geometry equal to 3. I'm sorry, number of electron regions equal to 3. And that would correspond to an electron geometry of what? Trigonal planar, right? Our number of electron regions will uniquely correspond to an electron geometry. So these are both trigonal planar. But in terms of our molecular geometry, what's this one going to be for its molecular geometry? Also trigonal planar, because there are no lone pairs on that central atom. So the two geometries are just going to match. All right, but now this one does have a lone pair on that central atom. So the molecular geometry will not be trigonal planar. Its electron geometry is trigonal planar. That's the way those electrons are pointing in space. But now if we go back here, I'll try to go back. Okay, if we take our trigonal planar electron geometry, but one of these is a lone pair, so it's invisible. We're going to go ahead and hide it here. So this is what this molecule would look like, right? It doesn't have all three bonds. It only has two. And that lone pair is pointed up, but it's invisible. It's just a group of electrons here. So this would be a different molecular geometry. This is what we call, they got real fancy with their terminology here. This molecule is what we call a bent molecule. All right, so what we're going to see is, while we're studying, we can take a look here. We have a little bit of a cheat sheet. We got a similar figure in our textbook. They're also easily Googleable here. All right, but for 3 electron regions, we have that trigonal planar electron geometry. If there are no lone pairs, then we also have a trigonal planar molecular geometry. All right, but if we do have a lone pair, all of a sudden, that lone pair takes up one of those spaces, and this molecule is what's considered bent. Okay, so if we have lone pairs on that central atom, our molecular geometry is going to differ from our electron geometry. All right, so then let's take a look at, we'll do some more similar examples here. So we said CH4. We're going to compare this to NH3. And then lastly, our good friend water. Okay, and again, we're going to determine the number of electron regions, the electron geometry, and then finally the molecular geometry. All right, so in each of these here, we can convince ourselves that these all have 4 electron regions, right? Whether they're all bonds, as in the case of CH4, or a mixture of bonds and lone pairs. All of these have 4 electron regions here. So if they all have 4 electron regions, that means they all share the same electron geometry, which would be what? Tetrahedral. Okay, but in terms of the molecular geometry, only one of these is going to have that tetrahedral molecular geometry. Which one would that be? The CH4, because it's got no lone pairs on that central atom. So if you have no lone pairs on the central atom, your electron geometry and your molecular geometry are going to match. All right, and so again, I'll post this video so you can get a better idea of these shapes. I thought the program was going to be helping us out here. If we look at our perspective drawing again here, Okay, again, this is for our tetrahedral. This is a common way of displaying geometries in chemistry, these dashed and wedged bonds. But now what I'm going to do is I'm going to get rid of one of these bonds because it's actually a lone pair here. And so what we get now is this little tiny triangle-based pyramid. It's not a very big pyramid. It's pretty squat, but nonetheless, it's got a triangle base to it, and it's in this little pyramidal shape. So we call this a trigonal pyramidal geometry. And if we erase two of those bonds to replace it with lone pairs, we're back to just that bent geometry that we saw earlier. Okay, so the electron geometry for all four of these is going to be that tetrahedral geometry. But if we have one lone pair on that central atom for our tetrahedral geometry, electron geometry, our molecular geometry becomes trigonal pyramidal. And if we take away two of those bonds and replace them with lone pairs, our tetrahedral electron geometry turns into a bent molecular geometry. Okay, so now we're going to keep going on this table here with 5 electron regions and 6 electron regions. These are considered sp3d and sp3d2 hybridized central atoms here. But before we can do that, we got to talk about one more thing with regard to drawing our Lewis structures. Okay, so we'll come back to this table and fill this in here, but we got to learn about what's called the expanded octet. Okay, so it turns out that large atoms, and by that I mean row 3 and below, can sometimes fit up to 12 electrons in their quote-unquote octet. All right, so there are certain elements, they're going to be our larger elements on the periodic table here, that will violate our octet rule. They'll have more than 8 electrons in their octet. And that's okay. That's perfectly legal because they're these big atoms that can accommodate these more electrons. All right? So let's just take a look. And the good news is that in terms of drawing these, you don't have any new set of rules here. We're just going to follow the same procedure that we've always followed. All right? We're just going to have to see that when we have these larger atoms, we're not going to restrict them to that 8 rule. They can have up to 12. All right, so let's do 2 examples here. PCl5 and SF4. All right, both phosphorus and sulfur live in row 3 here. They're these larger elements. So we're going to see that these structures here violate our octet rule. But in terms of drawing them, you're going to follow the exact same procedure that we've always done. So let's do this first one together here. The first thing we need to do is calculate the number of valence electrons that are in this particular atom here, our molecule rather. So each chlorine has 7, and I got 5 of them, right? So 7 times 5, that brings me up to 35. Plus, how many does phosphorus have based on where it lives on the periodic table? 5. So 35 and 5 gets me to 40 valence electrons here. All right, we're going to put down our central atom. We're going to decorate it with all 5 of these chlorines. Now what do we do? We're going to bond those constituent atoms to our central atom. That uses up 10 of those electrons. I got 30 more. What's the first thing that we do with any leftover electrons? We're going to make the outside elements happy first, the outside atoms first. Each one of these chlorines currently has just one single bond, so 2 electrons. So I'm going to add in a total of 3 lone pairs to each of these chlorines. All right, and that uses up all 30 of my remaining electrons. Okay? So that last step is we ask ourselves, is everybody happy? And this is where this expanded octet rule is going to come into play here. Because we're going to look at those chlorines and we're going to say, yep, those chlorines are happy. They all have 8 electrons in their octet, right? When we look at this phosphorus atom, though, how many electrons are in its octet? It's got 10 electrons in its octet. All right, but that's okay. That's allowed because phosphorus is in row 3 or below. It's one of these larger atoms that can have these expanded octets. All right, so bottom line is we're just going to follow the same rules we've always followed. But when we get to the end, if we have one of these larger atoms in the middle and it has more than 8 electrons, up to 12, that's okay. All right, so this is what's called the expanded octet. And I guess let's just also make a rule. Right, so it can have up to 12 electrons in its octet. This is for the central atom only. Okay, you're not going to load up the constituent atoms with a whole bunch of electrons. We're talking only about the central atom here. Okay, so again, following our normal rules, draw me the Lewis structure for SF4. All right, and if that sulfur at the end of the day has more than 8 electrons in its octet, that's okay because it's a central atom and it's larger than row 3. All right, so I total up my number of electrons here. How many electrons do I have to work with? 34? Is that right? Okay, excellent. I'm going to put my sulfur in the middle and my fluorines on the outside. I'm going to connect everything with single bonds. So that means that I put down a total of 8 electrons there. So that leaves me with 26 to go. I'm going to make everybody on the outside happy first, right? So then I'm going to go 1, 2, 3, 4, 5, 6. And I'm going to repeat that for all 4 of these fluorines. Right? Making everybody on the outside happy first. So now all my fluorines are happy, and I put down a total of 24 electrons. But I still have 2 left over. The outside's happy. What do I do with anything that's left over at this point? Put them on the central atom. And so if we count, again, my sulfur has a total of 2, 4, 6, 8, 10 electrons in its octet. But that's okay because sulfur is one of these larger elements that's allowed to have this expanded octet. All right, so this isn't going to influence how we draw our Lewis structures. We're going to follow the same procedure we learned how to do before. Right? The only thing it's going to change is that last check step where we look at the middle, and as long as it's one of these larger elements, it's okay if it has up to 12 electrons in its octet. All right, so then these things here with these 5 electron regions, I guess that's my next question. How many electron regions are in each of these molecules? Kind of gave it away there. 5, right? So my 1, 2, 3, 4, 5 single bonds. And my 1, 2, 3, 4 bonds, but then that lone pair. Both of these have 5 electron regions. All right, so the electron geometry for a molecule with 5 electron regions is what's called the trigonal bipyramidal. Pyramidal geometry. All right, so that is this shape right here. Okay, so if we look in this direction here, we have a triangle. Okay, if we look here, all right, let's actually just get rid of one of these so we can see it a little bit better. Okay, if we look here, we would have this triangle-based pyramid. If we connected all of these atoms here, we would have this little pyramid shape with a triangle at the bottom. All right, so then if I can figure out how to undo that, I'm just going to have to reload it. Okay, so when we have both of them here, we have 2 pyramids stacked on top of one another, back to back, what's called this trigonal bipyramidal geometry, right? So basically, I feel like this is going to be a disaster to try to sketch out, but let's give it a shot here. We have one triangle-based pyramid, but it's stacked on another triangle-based pyramid. That's that trigonal bipyramidal. That's where that name comes from. All right, so you can imagine a pyramid on top of this molecule with that triangle base and a pyramid on the bottom with a triangle base. So then which of these molecules, they both have an electron geometry that's trigonal bipyramidal. All right. What about the molecular geometry? Okay, which one of these can we fill in the molecular geometry for? Yeah, the PCl5. This is also going to be trigonal bipyramidal. But now for my other compound, my SF4, now I have a lone pair on that central atom. So its molecular geometry is going to differ from its electron geometry. All right. If we go and we get rid of one of these atoms on the side here, this is what they call a seesaw. Seesaw geometry, huh? Look, I got no idea because sometimes when they're naming them, they're like, let's pick the most boring Latin name for a geometry that we can possibly think of. Trigonal bipyramidal. And then other ones, they're like, it's bent. It looks like a seahorse, or sawhorse. I don't know. But anyways, this is what we call the seesaw or sometimes sawhorse geometry here because it looks like a little seesaw. Okay, so now let's do another one here from scratch. I'm going to give you the formula, ICl3. You're going to give me everything that we would have studied up until this point. You're going to give me the Lewis structure. Then you're going to count the number of electron regions. And from there, you're going to give me the electron geometry. And then we'll work to fill in the molecular geometry. All right, so I could put down my iodine in the middle and I decorated it with these 3 chlorines and I drew those single bonds, getting rid of 6 of my electrons. So then I made everybody on the outside happy, putting lone pairs on those chlorines, putting down a total of 18 electrons. And now I got 4 left over. Where are those 4 left over going to go? That central atom. Okay, and so if I look here, my iodine has 10 electrons in its octet. Is that okay based on where iodine is on the periodic table? Is it larger than row 3? Yeah, it's humongous, all right? So yes. So in terms of the number of electron regions, how many electron regions are there in this molecule? 5, which means it's electron geometry. That trigonal bipyramidal. All right. So now I have 2 lone pairs. Okay, so if I get rid of another one of these here, replace it with an invisible lone pair, we have this thing here. Can anybody guess what scientific name they gave this molecule? A T-shape. Yep, this is a T-shaped geometry right here because it looks like a T. All right. So then lastly, we can even have one more. So these all had 10 electrons in their octet. Just to go quick, we could also have, for example, SF6. This is a sulfur with 6 fluorines around it. And so in this molecule here, my sulfur has 12 electrons in its octet. And that's the maximum you're ever going to see, but up to 12 is allowed. Okay? So then if this molecule here, we get these 12 electrons in our octet, what's going to be the number of electron regions that we have in this molecule? 6. All right, so let's complete our table here. Okay, this is what's called an octahedral geometry. An octahedral is how you space 6 things out evenly distributed in space. And to just show you here, dang it. All right, so this would be an octahedral geometry. Okay, so obviously these shapes are very hard to sort of imagine in 2 dimensions. It's nice that you can like take them and spin them around like this. There are these things called model kits in chemistry that are used to visualize geometries a little bit easier. But of course nowadays, because of computers, there is some fancy technology kind of like this one here. In particular, there's a free program from the University of Colorado called a PhET simulator, and that's going to be part of your homework, is to work with that simulator program to build these molecules and spin them around in space to get a better idea of what these geometries are, right? We want to be able to connect these ridiculous sounding words like trigonal bipyramidal to what this molecule actually looks like. Taking it and spinning it around, believe it or not, is like really helpful for your brain to wrap around what the heck it's looking at shape-wise, all right? So part of your homework is going to be playing with that simulator app, and that you'll be able to find that on Canvas. Cool.